Welcome and Assalamualaikum to Madam Nur Ashikin. We are from Group 4 will be presenting the population growth in Bermuda, which is Task 1 Bermuda and Task 2 Question 4. So here are the members of the group. We have Ikhwan, Mariam, Tisha, Zaim, Aziza, and Hafi. So now let's start to travel to Bermuda's population.
Assalamualaikum warahmatullahi wabarakatuh. Today I want to talk about Bermuda's population growth. First of all, Bermuda is a British overseas territory discovered in 1505. Just 40 kilometers long and barely 1.6 kilometers wide. This small island is rich in culture with a population that 54% is African descent and 31% of European. Despite its size, Bermuda is densely populated 3,210 people per 2.5 square kilometers. Now, let's bring in the Malthusian growth model proposed by Thomas Malthus in 1798. It assumes population grow exponentially while food supply grow arithmetically. Using this model, our goal is to solve Bermuda's population equation from 2000 to 2019, predict future population after 2019, estimate past number, and analyze how this island nation is truly growing.
Okay. So let's move on to the table of data for the Bermuda's population growth. So this table shows the population data from the year 2000 to 2019. The second column, label T, represents the number of years since 2000, while the third column lists the population of the year. From the year 2000 to around 2007, we can observe a steady increase in population, rising from 61,550 to 63,010. After that, the population continues to grow, but at a slower rate. Between 2010 and 2017, the population stays fairly stable, fluctuating slightly around 63,500. In the last 2 years of this table, 2018 and 2019, the population begins to rise again, reaching 64,107 in 2019. This data suggests gradual growth over the 2 decades, with some periods of stability in between. So now I want to explain to you about our particular solution. So the first one is we need to write a general equation. It's dp over dt proportional to p. Then we need to put k. K represents a constant in population, so we get dp over dt equal to kp. And we bring p to the dp and then dt up to k. So we integrate both sides and we get integrate 1 over p dp equal to integrate k dt. Then integrate 1 over p, we get ln p. Integrate k dt, we get kt plus c. So the equation ln p equal to kt plus c. So we need to eliminate the ln. So we just add exponent to the both sides and get p equal to e power of kt plus c. And then
so now we want to determine the value of the constant. So the initial condition t equal to 0. The population is 61,550. So just substitute the value of p and we get a equals to 61,550. So the general solution becomes p equal to 61,550 exponent kt. So now we want to determine the constant k by using t equal to 1. So the population in 2001 is 61,867. So we just substitute the value of the p and then rearrange the equation to get k. So the answer is we get k is equal to 0.00514. So the particular solution now becomes pt equal to 61,550 exponent 0.00514 t.
So let's see the graph. So we have 2 graphs. On the left side is the original graph for the population, and on the right side is graph exponent for the particular solution. So the graph on the left shows population growth over time, starting from the year 2000. It uses data points to represent population at different years. we can see a general increase in population followed by a period of stability and then a slight rise again. The graph on the right, however, looks very different. It shows a sharp and sudden increase in values, which doesn't resemble real population trends. This graph most likely represents a mathematical function rather than actual population data. In summary, the left graph represents realistic population changes over time, while the right graph shows a theoretical and mathematical model.
Okay, so we applied the particular solution to predict Bermuda's future population and past population. We're using particular solution, which is PT equals to 61,550 exponent to the power of 0.005140. For the future, we use T equals to 20, which is in the year of 2020, and we got 68,214. For the past, we use T equals to 3, which in the year of 2003, and we got 62,506. Okay, now moving on to the analysis and discussion. Are the values calculated from the particular solutions accurate with the actual values? And the answer is no. The estimated values were a bit off from the actual population. This could be because of the small rounding differences in the calculations. Also, the time period used in the model might not match the real data exactly, which could explain the difference. Next, we calculated the percentage error, and we got 0.18%. Okay, so why is there a difference between the actual value and the estimated one? So there are a few possible reasons. First, unexpected real-world changes. The model might not account for sudden events like natural disasters, economic shifts, migration spike, or health crisis like pandemic, which can affect the population. Second one is estimation and rounding. The data used in the model might involve rounding or estimated values, which can lead to small differences. And the third one is model limitation. A first-order differential equation assumes a constant rate of change, but in reality, population growth can speed up or slow down at different times.
You may ask, what has affected the population growth in the past? Between 2010 and 2016, over 1,000 Bermudans left the island, mainly due to limited job opportunities, high living costs, and the pursuit of better education and careers abroad, especially in the UK, US, and Canada. This led to a shrinking workforce and aging population, and reduced consumer spending and tax revenue, adding strain to Bermuda's economy. In a small country, even modest immigration can have a significant impact. Bermuda's declining birth rate is largely driven by social and economic changes, greater access to contraceptives, and the rise in the women's workforce participation have given individuals more control over family planning. Many women now prioritize higher education and careers, often delaying or foregoing marriage and childbearing. According to 2010 census, Bermudan mothers are having children later in life. The shifts in lifestyle and gender roles have contributed to lower fertility rates and shaped the island's population trends. What do we think might affect the population in the future? There will be a lot of factors that might affect the population of Bermuda in future. Firstly, migration. If more people move into Bermuda for work or lifestyle, the population could grow. But if many live for better opportunities elsewhere, the population may shrink. Second, birth and death rates. A lower birth rate or a higher death rate, especially in an aging population, can slow down growth or even cause a decline. Thirdly, economic and government policies. Job availability, cost of living, and government policies play a big role in whether people choose to stay, live, or move to Bermuda. Lastly, environmental factors. Issues like climate change or rising sea levels could make Bermuda less livable in the long term, pushing people to relocate. Done.
Good morning, everyone. So this question was given by my lecturer to solve using the trapezium rule in Excel. We were asked to approximate the area under the curve for the function fx equal to square root 3 to the power of pi plus x times with ln in bracket 4 minus x over the interval x equal to -2 to x equal to 2. So first, I used n equal to 8 subintervals. That means I divided the interval into 8 equal parts. So my delta x is equal to 0.5. For each x value, I use Excel to calculate the function using the given formula. Then I applied the trapezium rule, where the first and last values are multiplied by 1 and the middle values are multiplied by 2. This is because the first and last values only appear in one trapezium, but the middle values are shared between two trapeziums, so they get counted as twice. After multiplying and summing everything, I use the formula area is equal to delta x divided by 2 times with the total sum, which I get approximately area under the curve is equal to 29.0845. Next, I repeated the same process with n equal to 10 sub-intervals. Now, my delta x is equal to 0.4 and the area came out to 29.0733, which is slightly more accurate because of the increased number of trapezium. In conclusion, Excel helped me quickly calculate values, apply the multipliers, and get the final area using the trapezium rule. We also saw that increasing the number of sub-intervals improved the accuracy of our result. That's how I solved the problem using both mathematics and technology.
First graph, n equals to 8, the sub-interval width is 2 minus negative 2 over 8, and we got 0.5. You can see the 8 trapezoids of equal width, each spanning 0.5 units on the x-axis, fit to the curve. The straight line tops of the trapezoid sometimes lie above the red curve and sometimes below it. This coarse fit leaves noticeable gaps between the polygonal roof and the actual curve. For the second graph, n equals to 10, the sub-interval width is 2 minus negative 2 over 10, and you got 0.4. Now there are 10 narrower trapezoids that each cover just 0.4 units in x. To improve the approximation, the slimmer trapezoids track the red curve more closely over and underestimates are much smaller. Visually, you can see the polygonal outline hugs the curve tighter, reducing the total error area. To sum up, we were able to achieve the goals of Task 1. We learned how to estimate the population of Bermuda using the Malthusian growth model. Although the estimated and actual populations were slightly different, this is expected because there are other factors that can affect the population. Task 1 was helpful because it taught us how to use math to solve real-life problems and how to explain why our results might not exactly match the actual values. The objectives for Task 2 were successfully achieved. We learned how to find the roots of a complex function using trapezium rule. In addition, we are now able to plot the graph of the given equation effectively using Desmos software and using Excel functionally. Overall, both tasks were completed successfully.